introducing the topic.
Yep. Paul, are you able to share your screen?
Yeah, I'm just trying to remember how to do it on Zoom. We normally do Teams, so I'm a little bit backwards on Zoom. But there we go. It's not that much of a problem.
Mm-hmm.
Right.
I think we'll just give everyone a few minutes to come in before we start the session.
Okay.
How can I move my thing? Oh, okay. Your dog.
Come here. Good boy.
Should we wait one more minute?
Up to you guys.
Yep, I'll wait one more minute. Okay, I think we can get started now. Hello, everyone. Climate X Change is back, and welcome to our first event, which is episode 1 of Carbon Capture and Storage. I hope everyone is enjoying spring term or is trying to. Today, we have Professor Paul Fennell here with us, and he is a clean energy professor here at Imperial, who taught Ferdinand and I in our undergraduate. And today, he'll be talking about industrial carbon capture technologies, as well as further research in this area. So unlike our usual sessions, we will not be having breakout rooms today for both our carbon capture episodes, so next week as well, because they're a little bit more technical. But we will have a Q&A session after, and if your questions are quite short, then Paul will just answer them as he goes. And so pop your questions in the chat if you have any. And just to let you know that this session is recorded, and without any further ado, let me pass it on to Professor Paul.
Okay, hello everybody. Can you hear me? You still hear me? Yes, right, good. Just wait 1 second. You may hear some whining in the background. I promise that this is perfectly reasonable, but my dog is in my room at the moment and he's a little bit unhappy. So if you hear any whining, that's just the dog, but I'm sure he'll be all right.
Sorry, Paul, we're seeing the presenter screen. I think you need to switch it to the PowerPoint.
Oh,
at
you're
some
seeing...
corner of your screen. You have to
God.
like switch display setting on the top left, I think.
Right.
Yeah. Okay, cool. You're good.
You're seeing this screen, yes?
Yeah, we're seeing the right one now.
Okay, so without further ado, and without further apologies for the dog, I will get on with it. So what I'm going to do is I'm just going to roughly talk through a few different things about carbon capture and storage, why it's necessary, a couple of different types of CCS, and then application of CCS to the major industries that it's significantly applicable to: cement, iron and steel. And then I'll talk about biomass enhanced carbon capture and storage, which allows you to suck CO2 out of the atmosphere. And then I'll talk about some of my views for the future. There's a few people that disagree with my views. Well, they're entitled to their opinions, but they're wrong. Right, okay, so why do I work in CCS? Well, in order to sort of get a bit of an idea of why to work in CCS, you have to think about why to work, what an integrated assessment model is. So these are what the government, you guys probably done integrated assessment models? You can just put your thumbs up. Yes, yes, right, good. So CCS is a system which allows you to decarbonize some particular industries that are very difficult to decarbonize otherwise. So that would be iron, steel, and cement. And it also allows you to retain some flexibility of electricity supply in your system that otherwise you would not be able to. This means that integrated assessment models very much choose CCS, and that's an important thing that allows you to say, well, actually this technology should be something that needs developing and should be something that we'll work on. So, as I've said before, CCS can be integrated into the existing energy system without making large changes to the overall system, right? So if you're using a particular fuel mix and then you just add on carbon capture and storage, you have the potential to continue using that. Now, in the UK and around the world, we also seem to be, which is good, moving away from coal as a fuel. I told my clean fossil fuels students this year that this will be the last time I'd be lecturing on coal utilization, because I think that the world needs to move on from it. There are issues as well with renewables. I'm not saying that renewables aren't important, and I'm not saying that renewables aren't, in many ways the future. But as you put more and more renewables on the system as a whole starts to become more expensive because the renewables reduce your ability to produce electricity in a flexible manner, so to match demand and supply. If you're including industrial sources of CO2, CCS is one of the only ways to actually decarbonize those emissions. So cement, and to a lesser extent, iron and steel, actually produce very large amounts of CO2 as part of the actual intrinsic chemistry of producing cement or iron and steel. And that means that you have a big problem if you want to decarbonize cement without actually having carbon capture and storage. Then you've got some other emissions that are very expensive to decarbonize, including, for example, air travel, although global pandemics seem to have done quite a good job of reducing air travel. And actually, we'll probably be doing a lot more video conferencing from now on. Well, maybe as soon as we're allowed to actually travel again, everyone's going to be, hey, let's go travel. But assuming that, things calm down again after that, maybe we'll be going down to a bit lower level of air travel anyway. But it's extremely expensive to decarbonize air travel. And, all this culminates in the integrated assessment model saying that, you need nuclear, fossil, CCS and bioenergy. So, there's reasons why we work in the area. In particular, here's some results from the IPCC in November 2014, and this is the increase in the total discounted mitigation costs to 2100 relative to the default technology assumptions where every technology is actually allowed. And if you see here, for a 450 ppm CO2 equivalent, not having CCS in the system gives you 138% increase in the discounted mitigation costs. If you say, well, you're not allowed nuclear, that only increases the cost by 7%. Limited solar and wind only by 6%, and limited bioenergy also has a significant role. So CCS is the technology that, of all the technologies that you could possibly develop, it's one of the ones that we really, really need to develop to get a least cost solution to mitigating climate change. So we're going on to the industrial arena. So there's different types of flue gas or exhaust streams from different processes, and it's really important to remember that the composition of CO2 has the composition of CO2 is variable, and also the pressure that the streams would come off is also variable. So here I've plotted on a logarithmic scale the partial pressure of CO2, and for a variety of different off gases. You'll see that gas turbines around here have about 3% CO2 in their exhaust, but sorry, well, they are at atmospheric pressure, but okay, 0.3 bar of CO2 in them, and sorry, 0.03, God, can't read a diagram today. And a blast furnace has, quite a high partial pressure of CO2. And what this effectively means is this is much more easier. You can see the arrow on the screen, yes? Yep. This, not anymore. This is much easier to capture CO2 from this, all other things being equal. Although refineries have sort of, some nasty H2S and things like that in as well. I think that's all I need to, and whenever you're actually thinking about carbon capture on a process, you need to think about both the CO2 partial pressure, any minor species that are in there, and also the sources of heat in the system. It's really important to be able to think about how much heat there is available for you to drive your carbon capture process. So even though this is a lot easier to capture, or should be a lot easier by thermodynamics to capture CO2 from than the gas turbine, because the gas turbine doesn't have any nasties in its exhaust, and because there's no nasties in the exhaust, and because the gas turbine has significant amounts of low-grade heat that you can get at to help you to regenerate your solvent, it turns out that the gas turbine is not that much more difficult than the blast furnace. So it's a case of you have to look at your process, look at the sources of heat, look at the different contaminants in it, and then design a process for a specific industry. Lots of people just sort of say, oh, well, put amine scrubbing on the end of everything. And it's like, well, yeah, but that's going to be about twice as expensive. So to back that up, this is the costs of CCS, which we found from a survey of the literature. The size of the bubble indicates how many studies we found, and the color of the bubble tells you what the particular technology that we looked at was. And you can see, for particular reasons, there's a nice good synergy between calcium looping, which is technology that I work in, and cement production. And then all of these nice high purity sources down here where you're producing, so these are the ones in this quadrant of the diagram. These are the ones that are producing essentially a nice high pressure stream of CO2, or can be changed around so that they produce a high partial pressure, high pressure stream of CO2. Right, so those are the easiest things to capture CO2 on. And then other technologies, there's a variety of different prices depending on what particular technology you seek to apply. It turns out that it's very, very expensive to do amine scrubbing on cement plants, and that's why the first demonstration of CCS at scale is on at scale on cement plants uses amine scrubbing. They'll get there are some issues with other technologies. The major issue is that you need to get a vendor to give you a guarantee that the thing will work as it should, and the vendors will give guarantees for amine scrubbing. So there's a lot of incumbent advantage for those technologies. Anyway, never mind, at least they'll be demonstrating something. Right, so one thing that is important that I alluded to earlier is the value of additional capacity. For different technologies, looking at the cost of the system as a whole, it turns out that as you put extra chunks of capacity, I'm talking here in terms of electricity generation, as you put extra chunks of capacity on the system, the cost of the system overall starts to increase. It's a particular problem with renewables because renewables can't match supply and demand in the same way as fossil can. So here is a plot which says, right, over here we have 85 grams per kilowatt hour electricity in 2030. And we want to add on different technologies and see how much they increase the system cost by. So as we add on a chunk of 5 gigawatts, the system cost starts to increase by significant amounts. So marine's expensive and doesn't actually get that much more expensive. PV significantly has an upturning curve the more you add on. So PV isn't that expensive to have a bit on the system, but starts to become more expensive as the amount that you put onto the grid increases. And that's because it's all highly correlated. And you have day-night issues, you produce a whole load of electricity in the day, et cetera, et cetera, et cetera. Offshore and onshore wind are generally all right. And then here you've got the CCS options. And the CCS just acts as balance of supply and becomes, it very little changes the cost of the system. But there here is a bit of a limit to how much you can put onto the grid, although that's not the same with nuclear. Nuclear, you can actually put a vast amount on. And biomass basically costs very little to put onto the system because the biomass helps to absorb supply and demand issues elsewhere. And it's not that much more expensive. So that's again why we're interested in CCS. Partial pressure, right? Partial pressure is the concentration of CO2 in terms of fractions of a bar multiplied by the total pressure. So if you have a stream at 10%, and it's at 1 bar, then its partial pressure is 0.1 bar. If it was at 10 bar and it was still 10%, the partial pressure would be 1 bar. That's what's actually important when you actually look at the thermodynamics of the systems. Marine here is like offshore, the turbines that go under the water and that sort of stuff, and probably a bit of wave and all that sort of stuff. Okay, I will talk about heat and CCS efficiency and bioenergy later during the questions, because it's a bit complex to just answer quickly. Right, so having said that there's different types of CCS, here's a basic example of common or garden CCS, and this is what you'll see on the pilot plant next week. Although it doesn't have the power plant stuff, we just have some CO2 that we recirculate around the system because it's a lot cheaper. Right. Power station produces an exhaust gas with CO2. That's about 15% CO2 from a coal-fired power station, or maybe 3% from a natural gas-fired power station. It then goes into a scrubbing column. This will be a very large piece of equipment. You know, these four carbon capture and storage will be the biggest solvent scrubbers that have ever been designed. The gas goes in at the bottom and then flows up to the top, and a solvent flows in at the top and goes down to the bottom. The ex-chemical engineers are starting to go, oh, I remember this with pain. All right. What that means is that comes out of the bottom is a CO2 rich solvent. So the CO2 has gone from the gas into the solvent. And then here we have our solvent regeneration column. And we put energy in and boil off the CO2 essentially. And then we have pure CO2. We then compress the CO2 because we want to transfer it in pipelines, and pipelines are much more efficient if you're using a liquid. So we compress it either to a liquid or a supercritical fluid, and then just send it off to storage, where it just gets put under the ground. It's a couple of kilometers under the ground, and safely stored. I'm not going to talk about CO2 storage because it's a huge area in its own right, and I suggest if you're actually interested, you get a different speaker, because that's not me. Right, now the energy input, this is the time to talk about the energy input. The amount of energy that you put in here, this comes from steam in the power plant process. This comes from steam that is diverted from the power station, right? So it's steam that would otherwise be going through the low pressure turbine. In a power station, you've got three turbines. You've got a high pressure, an intermediate pressure, and a low pressure turbine. And the switch over between the intermediate pressure turbine and the low pressure turbine is where the steam is extracted to do this regeneration. And you have to take out quite a lot of steam from here, but it's already gone through the high pressure and the intermediate pressure turbine. So you've taken a lot of, you've made a lot of electricity, but it, you know, maybe 30 or 40% of it doesn't go through the low pressure turbine. Then you, right, so, and because of aspects of thermodynamics that I'm not going to go into, it turns out that this is actually quite thermodynamically a reasonable way to do this, right? Essentially, you've got a heat source that, though it's not perfect, you've taken out most of the work from it. So yeah, it's reasonably efficient, right? Just to say, to answer the question, the CO2 solvent would probably be monoethanolamine or a blend of monoethanolamine, MEA, and other stuff. Also, it's got a lot of water in the system here to prevent corrosion of the process. This is cyclical, right? So, you know, it comes along, picks up CO2, goes here, the CO2 gets stripped off, goes back to the process, and then cycles around. So not too much of a problem. It can degrade as a function of time. And what you do with it then is you generally, in a lot of cases, they will put it through what's known as a reclaimer. So it forms some gunk, and then you can actually reverse the reactions that have led to it forming gunk and make it nice. And if you can't reverse the reactions and make it nice again, then you have to just dispose of it as a waste. But it's a cyclical process, so it's not a huge problem. And there's been some commercial deployment. There's been a system in operation at Boundary Dam in Saskatchewan. It's shut down now, but it did demonstrate the process reasonably well. And the reason that it shut down was nothing to do with the process. It was to do with the cost of CO2. So CO2 is valuable for a number of different uses, but if your global oil market starts to decrease, one of the biggest ways that you can use CO2 is to do enhanced oil recovery, EOR. And if the global oil market goes for tanks, then your CO2 price suddenly becomes very low, and you can no longer really afford to sell it. So that's basically what happened here. Right, I won't go through all the different pros and cons, but if you're interested, you can look at different ones that are here. One thing that is important to say is that there's a number of different solvent package suppliers out there, and each of them has developed their own proprietary technology. So MEA on its own actually is what people used to use, but there are better blends that have been made up which can give you a better overall outcomes. Essentially, you can add in other materials which improve the property of the MEA, and in particular there's a important role for corrosion inhibitors, which will prevent corrosion going on. The cons of MEA: there's a high capex for the process. You do reduce the thermal efficiency in the system by about 20% of the output from your power station. So that's not an insignificant amount of loss of power, but then you're not producing the CO2. And that's basically it. I won't go into this. You can lose some solvents. There's a potential for loss of solvents to the atmosphere or to the environment, but you need to just be clear that you can, if you design your process properly, you won't have any loss. Oh, Ollie dog. Right, he's very sad about the potential for loss of amines to the environment. Right, so some of the things that people are working on at the moment are things like these supported amine solids, right? So instead of having a solvent going around your system, you have an amine which is supported on a carbon shell or something like that. It does the same thing, sucks up the CO2, releases the CO2, but can be used at lower temperatures for the regeneration. The lower temperature for the regeneration in this process is good because you have to take out your steam here at a lower temperature, and it turns out that that means you can let more of it go through your low pressure turbine. And it's easier to prevent any losses of material because the amine is actually physically on the surface of the solid material. Right, another way of doing CCS is to do oxycombustion, and this is pretty simple. You burn the, you have an air separation unit, you separate air into oxygen and nitrogen, you put your oxygen into your power plant with some CO2 that you're recycling, and you basically produce a pure stream of CO2 and steam. And then you just condense out the stream and you've got a pure stream of CO2. Nice, simple, was planned to be demonstrated at scale in the White Rose project for Alstom in the UK, but it was pulled under the last when they pulled the plug on the last CCS demonstration project. So that basically tells you what I've said there. It has some significant benefits. It's a bit more complicated in terms of the fact that it changes your burner, not the composition, but it changes the burner properties because you're using CO2 instead of nitrogen to as the balance of your gas, but works pretty well. The efficiency penalty there comes from the fact that you have to separate oxygen, but other than that, it's fine. Right. So that's a flow sheet, and I won't go into the details there. Right. Air separation, just to say, it's a technology that's been around for a very long time and can be done at huge scale. So there's no real issues with that. And large scale, Praxair, has very large numbers of ASUs operating worldwide. The Collide project was a large scale demonstration of oxy-fuel CCS, and it was in Australia, and reasonably going well, I think. So moving on, so those two were probably the main technologies that you could just go and buy right now, although there's other ones that you can buy if you're looking at doing pre-combustion capture, which I'm not going to go into. But pre-combustion capture, you could buy Selexol or Rectisol based technologies, and that would sort you out there, but I'm not going to go into what they are. So what I've been researching, or I'll say what I've been researching for the past 15 years, but I gave up researching this after about 8, because I essentially considered that we'd solved everything that was important and it just needed to be demonstrated. Didn't go down very well when I basically stood up and said that at the conference on this technology. I don't know. I basically said, why are you wasting your lives? Right. So not to say that it shouldn't be deployed. It does need to be deployed, but no further development required. Combustor here produces a flue gas. Here goes to a carbonator. Here calcium oxide reacts with CO2 to form calcium carbonate. Highly exothermic reaction here gives out a lot of heat. That heat can then go into a steam cycle and produce electricity, which means that your system as a whole is quite efficient from a thermodynamic ground. The calcium carbonate that you formed here goes into a calciner, where oxygen and coal from an air separation unit go to the calciner and burn and produce heat to reverse this reaction. Highly exothermic, highly endothermic. But what we're actually doing is we're burning coal with oxygen and borrowing some of the energy to split CO2. When you actually do the calculations, this ends up being exceptionally efficient if you want to produce electricity as well. So that's good. The other thing is that this calcium oxide purge is can go straight to a cement plant, and the main material that you use on a cement plant is calcium oxide, and that means that you can actually then decarbonize the cement plant, but without actually having to put on CCS onto it. I'll discuss that in a bit. This is the problem of all of the technologies that we're looking at the moment. As you keep doing research and as you keep doing development and deployment, you get up to a stage up here with the first of a kind commercial scale plant, and your costs are the most that they're going to be. And then after that, you learn in a commercial sense. So this is research and development. This is commercial deployment. And as the system gets more mature and you have, you know, hundreds of plants, the costs come down significantly. This is a curve that is well known in a number of settings. And essentially, to get over this hump requires a lot of money, and that either comes from the governments or it comes from the companies themselves. But the companies will only put it in if they truly believe that climate change mitigation is going to be a thing that has to happen, right? And you'll note that this was like 2015. Right, so why aren't we doing it? I don't expect you to read the writing. Why aren't we doing it? It's because governments don't necessarily give confidence to people that there will be climate change penalties that are sufficiently high that anyone might actually build a CCS plant, right? So the costs of these sorts of things are maybe 60 or 70 pounds a ton of CO2. And at the moment, it's just so much cheaper to just throw the CO2 into the atmosphere. That's what everybody does. If they thought that they were going to get a tax of maybe £100 a ton or something like that, then they would start pushing the technology over that hump. But we're not there yet. We're starting to get there. I think one big thing that's going to happen fairly soon is I think China is going to start taking more of a lead in climate change negotiations, and then I think that the rest of the world will be, more involved. Also, obviously, we've got rid of the idiot in the White House, so we've got a different person in there who has less idiotic views on climate change, well, on basically everything. Sorry, little bit of you might know a little tiny bit of politics moved into my presentation there. You're all doing a environmental technology MSc. I'm fairly sure there's few people that take that go, Trump, he sounds like an excellent leader that will be progressive in environmental policies. Right, big other issues, liability, right? So you have got this CO2, you've pumped it under the ground, and it's there. Who then takes over from the liability for that CO2 20 or 30 years in the future is a big issue, because at some stage the operators want to move the liability from themselves to, obviously, they'll be insured, and the insurers want to, change the very long-term liabilities going back to the state. So that was an issue. It's a soluble problem. I mean, at the end of the day, the state will have to be the insurer of last resort on any of these things. Public and political perception is a significant issue, not in the UK, not probably in the US to such a big extent, but a lot of places in continental Europe really don't like the idea of storing CO2 under them, and tend to protest and all this sort of stuff. This led to Germany essentially banning it and trying to ban it across the EU, particularly in the EU green climate bonds, which were recently developed, but CCS did manage to get into it. People worry about accidental leakage, but as I say, the stuff's 2 kilometers underground, and provided you actually store it pretty well, there's not going to be a problem. In So Guy's question, what's the alternative to storing CO2 underground? There really isn't one. You know, if you're going to do carbon capture and storage, you have to store it underground. I'll discuss CO2 utilization in a bit, and you will recognize that it is a terrible idea. Right, so I was part of this, and I was in charge of the cement part of this. So here is a cement plant, right? At the top, this raw meal is limestone. You put it in, it goes through a variety of cyclones. You've got gas coming up here from this burner where it's very, very hot. And the purpose of these cyclones is to transfer as much energy that's still in the hot gases exhausting from the cement plant to the particles as they drop down the system. Your exhaust gas here, maybe about 20% CO2. And then out at the bottom, you have your chemical reactions going on between your limestone and your other components. And at the end, you get this material called cement clinker, which is the main component that's in cement. So it's a countercurrent heating process with a bit of chemical reaction thrown in at the end. And the issue is that limestone is calcium carbonate, and the first thing you have to do is to change the calcium carbonate to calcium oxide. That goes on sort of in this part of the reactor. And that chemical reaction, calcium carbonate to calcium oxide plus CO2, if you want to have calcium oxide here, sorry, you don't have calcium oxide here. If you want to have calcium oxide here and make what's known as ordinary Portland cement, then you will have to have limestone going in here. It's an unavoidable part of the process. And 60% of the CO2 emissions for the process come from this bit, right? The calcination side. So 60% of the emissions for cement production come from the unavoidable chemistry of the limestone process. Now, lots of people talk about, well, why don't we make alternative cement chemistries? Why don't we do something that will, you know, have a different chemistry that will use less CO2 or anything like that? The trouble is that one of my friends in the cement industry basically said, get your cement, build a bridge, have the bridge stand up for 20 years. If it stands up, then people might want to buy your cement, right? So they're very, very conservative when it comes to changing the properties of the cement that they're using in the building trade, which, let's face it, is probably good because, you know, nobody really wants to be living in a building that falls down. And essentially, that's what this says. Any process other than carbon capture essentially leads to 60% of the emissions still being there. So even if you used hydrogen to run your calciners, even if you used electrical calciners, anything like this, you still have a huge amount of CO2 being produced. So, as I say, calcium looping links in nicely with this because you've got the calcium oxide coming off here. And so that's 60% of the emissions mitigated for your cement plant without even having to put CCS on the cement plant. So I also talked about iron and steel in the decarbonisation plan. And again, it's the similar process that because they use, because you reduce the Fe2O3 to FeO and then to Fe with carbon monoxide, which is formed from coking coal, you have issues with the actual fundamental chemistry of the process. It's not quite as bad because you can actually do this with hydrogen, but it's very, very expensive to do it with hydrogen. But, you know, chemistry in the iron making process. So what do I think is the future? I think we're probably going to move into the field of negative emissions. Part of the CCS story is going to have to be taking CO2 out of the atmosphere because we're going to put too much in, and because some things are very, very expensive to mitigate. So, here's a Mach curve. I mean, the trouble is that when you start talking about this, you do actually have to think about the fact that there's quite a lot down here in a Mach curve, and which we don't do. All the insulation stuff we still don't do down here that we should do. And, here is essentially, once you know how much it costs to take CO2 out of the atmosphere, anything up here that costs more than that, you would just take CO2 out from the atmosphere anyway. Right. Part of the option to achieve net zero, and here's the reasons that I've just said for taking CO2 out of the atmosphere. So easiest way to do it is to grow crops, take them to a power station, a bioenergy power station, capture the CO2 out at the end, and then compress the CO2 and take it to storage. So you've still got electricity production, you're generating it from biomass, you've not got the fossil fuels being used, and you're actually net taking CO2 out of the atmosphere, right? So winner, winner, chicken dinner. Turns out that it's also about 4 times cheaper than just trying to scrub the CO2 out from the atmosphere. If you remember my initial plot, you can scrub CO2 out from the atmosphere, and we're looking at some things at the moment where we're just directly taking CO2 out from the atmosphere. But the partial pressure of CO2 in the atmosphere would be somewhere down here, right? So very, very difficult to take out from the atmosphere. And, first off, you do CCS on all of this, and then you take CO2 out from the atmosphere. Although, what are we putting a lot of money into at the moment? CO2 from the atmosphere. Hey, rational decisions. BECCS. And if you look at IPCC projections, BECCS starts to become pretty important in later years because, here the biomass with CCS becomes pretty important, because essentially there are some things that you just can't mitigate. And, some of the, there's all sorts of weird and wild potential schemes that you can come up with. This is one of the ones that we published from my lab, where you can do things like produce ores, from iron ores, you can produce iron and hydrogen and all sorts of different things as well. So, integrating different processes together is a great way to make things more efficient, but more complicated. I won't go through this. Speaking of complex, not the future. I don't think CO2 utilization is going to be the future. And the reason I don't think the CO2 utilization is going to be the future is because if you look at the global uses of CO2 here, and the global and the annual production of CO2, you can see that the sources of CO2 outweigh all of the things that we can think of that we could take CO2 into by several orders of magnitude. People then say, well, why don't we make fuels using CO2? And it's like, well, firstly, learn thermodynamics. And secondly, because if you take if you take some CO2 from the exhaust of a power station or whatever, and then make a fuel out of it, so make methanol, put a whole load of energy in, react that CO2 with hydrogen, make methanol, great. First off, why didn't you just use the hydrogen in your vehicle or whatever? Anyway, you had hydrogen, why didn't you just use it? And secondly, the CO2 is going to be emitted when you burn that fuel in your car. So you are still emitting a whole load of CO2. So it's a silly idea. Right. There's other more fundamental issues that I can go into, but those are the main ones. It's temporary storage of CO2, and it's tiny amounts except for fuels, and fuels are stupid. So to conclude, CCS is an important part of the armory for decarbonising the planet. Different processes have different most appropriate technologies, and some industries simply can't be decarbonised without CCS. And the example that I always say is, you can't make cement from a wind turbine, right? So you can make, you can switch over 100% to renewable energy without CCS, but you're still going to have some high emissions processes that need sorting out. And we need to continue our D&D. And with that, I'll say thank you. Shall I just go through the question? I'll tell you what, I'll just go through the questions, blitz them out, because it will save, time. Slides will be shared after the session. Yes. And the recording. Yes. Why is bioenergy so important? Quite surprising it's more important than wind and solar. The reason that bioenergy is so important is because, again, it is if you're producing electricity from biomass, it's an electricity source that you can match supply and demand with. So if there's a lot of wind on at any particular time, you shut down your bioenergy plant. You don't produce electricity then. But when the wind's not blowing and the sun's not shining, you use your bioenergy plants, or you use your CCS plants, and you can still produce uninterrupted power. The key thing with any of this is that uninterrupted power is so much more important than the cost of not having power available when you actually need it is a great deal more than the cost in most situations of actually generating that power. It's a factor of 10 to 1, probably more, right? If you can't turn on your computer at home now, you're basically not productive, right? Whereas the electricity that's being produced is probably costing a couple of 2 or 3 pence per kilowatt hour. Right, heat did that, marine did that, partial pressure, yes. CO2 CCS storage speaker, speak to Branko Bujelic, I'm sure he'd help you. Ethanolamide, let me know if a dog walker. He seems to have gone to sleep. I put a blanket on him. If CCS successful, yes, Rob, if CCS successful, high dependent on CO2 price, do you see a carbon tax or CTS will be key to CCS's longevity? Yes, I mean, you're going to have to continue paying, or you're going to have to continue penalizing people for emitting CO2, or they'll just emit the CO2. Companies just do not do the right thing without some form of regulation, or most companies don't. Do I expect an official global platform for trading carbon credits and transfer? Sort of. Right. Do I expect an efficient global platform for trading carbon credits and or trading of free storage credits for strategic industries which cannot be re-engineered? So UK, for example, could buy CO2 from the EU. Now I'm sad. And store it. Yes, there is the possibility of doing that. Do I expect it? Probably not for transnational movement of CO2, because the EU will basically, the EU's got storage space in around the waters around the Netherlands and that sort of stuff, so they can do their own. Essentially, most of the coastal nations for the EU and surrounding hangers-on like Norway, anyone that can get to the North Sea is like, hey, we're just going to stick CO2 in under the North Sea. So, and thus the problem is solved forever. Everywhere that's like mainly got problems getting their CO2 to the North Sea, it's like, yeah, I think we should think more carefully about this as a problem. And maybe we should think more about CO2 utilization. I've had many, many long discussions over this. The alternative to storing CO2 underground is to let it go into the atmosphere. So as I say, I strongly don't think that CO2 utilization can work. From a technology scalability standpoint, how big an issue is the fouling in the carbonator for the calcium looping? It's not really an issue at all. We've got there's been a demonstration of the process. It's been done at 1.3 megawatt scale. It just wasn't an issue. Not a problem. So I'm saying that it's better than battery storage. I am saying that you can't prevent CO2 emissions from cement and iron and steel with battery storage. I think battery storage risks developing another industry which may well have significant environmental issues. I certainly do agree with batteries for many applications, and I very nearly got myself a Tesla Powerwall, but we couldn't really work out somewhere to put it. So I've got solar cells on the house. I'm all in for renewables, but I'm all in for, you know, everything as fast as we can everywhere, right? So you do battery storage, you do CCS, you do everything that's possible. And you do them very, very quickly, because I think we're coming up to, you know, super climate emergency. But in terms of battery storage, yes, I would. You know, it's an emerging technology. I think that it's going to be pretty useful in the future. Its costs are coming down all the time, but they have to come down a lot in order for them to beat out bioenergy. So, Guy, you were saying in reference to bioenergy, yeah, I mean, it's, well, these costs here will include costs for battery storage. So the you know, the baseline will have some storage of some battery storage within it. I guess it depends on how aggressively the price comes down. Again, I was thinking about getting one of the Tesla, you know, one of the newer, massively cheaper Teslas. But then my wife persuaded me that it would be much more environmentally friendly to continue not to have a car and to just cycle where necessary. And that's better for me, but more fool her, because nobody's going anywhere at the moment. So we just don't have anything. Right, I think that's all the questions answered. I think that's everything. And I think you're coming up to the hour. So I will allow you guys to break in, wish me great thanks, tell me how wonderful the presentation was, and get on to your next thing.
Thank you, Paul. Your presentation was really wonderful. I give you great thanks for your hour. Thank you very much.
Right. Cheers,
thank
everybody.
you, everyone, for coming. Next week, we have episode 2, where we're going to show you a tour of Imperial's Challenge carbon capture plant. So make sure to stay tuned. We'll let you know about the details. Thank you.
Cheers, guys. Bye-bye.
Thanks, Paul. Bye-bye.